Hi, I'm Brandon, and let's talk about SnarkyJS. I'm going to intro and then I'll pass it off to Jack. So I work at O of One Labs. I'm a founding engineer. O of One Labs' mission is to catalyze a new generation of applications powered by zero-knowledge cryptography. And we do that in a few ways. We built the Kimchi proof system, and you'll hear more about that later. We incubated the Mina protocol, and we recently launched SnarkyJS, and that's what we're going to be talking mostly about today. So let's talk a little bit about Near. So Near is building a layer one blockchain, and the Near community is exploring adding a ZK application layer for Near, and they want to use SnarkyJS. So because of that, the track was sponsored by Near Foundation, so thank you. But since the SnarkyJS layer doesn't exist on Near right now, we're going to use Mina instead. And SnarkyJS was built for Mina. Mina uses the Kimchi proof system natively, which SnarkyJS also uses. And so Mina is a really great place to use SnarkyJS and build ZK apps. So this track is one of 5 in the Berkeley Hackathon, and it's particularly well suited to folks that want to build applications with zero-knowledge proofs, because SnarkyJS uses web tooling, and anyway, Jack will talk about it. And it's a great place to build libraries as well, especially cryptography primitives and whatnot. So yeah, I mean, SnarkyJS supports infinite recursion in a really nice way, and I don't think any other tools do this at all. So yeah, hopefully that piqued your interest a bit. I'm going to hand it off to the brilliant Jack Servia to take it away. Go ahead, Jack.
Hey, so I'm Jack. I also work at Owen Labs. I do developer relations there and a little bit of engineering work. I'm based in Denver, Colorado, and my Twitter is Jack Serbia. So yeah, we're going to talk about SnarkyJS today. And SnarkyJS is a TypeScript library that makes working with zero-knowledge proofs easy. This is what a provable program looks like in SnarkyJS. And SnarkyJS is also the smart contract for Mina, an L1 blockchain. And here's what a smart contract looks like in SnarkyJS. It's basically the same thing as a program, but with some extra sort of stuff added on the side so that it can manage things like state. But we'll dive into this more in a little bit. For now, I'll keep it pretty high level. So you can see everything in SnarkyJS is TypeScript. So you can define circuits, generate proofs, and verify them all in a standard JavaScript runtime, like Node, Electron, Firefox, Chrome, and probably some other things. Plus, you can keep using the tools that you're familiar with, like NPM, Prettier, ESLint, VS Code. And SnarkyJS is also very easy to learn. You can see we've put a lot of effort into making the type doc coverage really good. So you can dive into a SnarkyJS code base even without sort of touching docs and just hover over things, and IntelliSense will usually give you a description of what the thing you're looking at is, and also some example code. The other thing about SnarkyJS is that it's extremely powerful. And this is basically for 3 reasons. The first is that it's a really well-designed language, but you'll get to see some of that later. The second is Kimchi, which is our proof system. And this has fully trustless setup. It's got custom gates for Poseidon, which is a hash function that's efficient in elliptic curves. It's got, a hash function that's efficient in zero-knowledge proofs. It has elliptic curve math gates. It has encryption and decryption gates and signature generation and verification gates. It has a constant proof size. It's just a few kilobytes. It's infinitely recursive with arbitrary branching and merging. And it's also plonkish. And this just means that we can sort of keep up with the research that people are doing there. We can add things like lookup arguments and other stuff like that as it kind of, as people discover new things. The sort of third side of SnarkyJS's power is just that all of the things that you implement, plenty of the stuff that you need is already implemented in SnarkyJS. So what we have today Well, we have, our fundamental type, the field, and then all of these other types eventually are represented as the field, but we have implementations for unsigned integers of 64 and 32 bits, integers of 64 bits, group, bool, scalar, public key, private key, signature, circuit string, and more in the works. This means that you can use types that you're familiar with, and these types, like for example, uint32 has a mod method on it, so you can work in a way that you're probably used to with another programming language. We have structs, which allow you to define your own types out of these existing types. And we'll look at some of those later in this presentation. Yeah, we have efficient Poseidon, elliptic curve, encryption, and signatures. We have a library for Merkle trees. We have this action reducer mechanism, which basically allows you to dispatch sort of requests to do something and then actually do those things separately. So you can kind of you can basically process things eventually. And kind of have a queue for what needs to get done. And then the Mina protocol also supports custom tokens at the protocol level. And so SnarkyJS, exposes a bunch of stuff so that you can work with these nicely. So why did we choose TypeScript? The reason is that we're ecosystem focused. You can see NPM published hard crypto library. And this is kind of the idea. We want to have code reuse that's as high as it is in the JavaScript ecosystem. And we think that a lot of really cool things can come out of that. Zero knowledge proofs open the door to lots of new kinds of applications. And especially if you start to pair them with, MPC stuff or homomorphic encryption stuff or whatever, there's sort of even more crazy stuff you can do. And the idea is that people who want to build, I don't know, libraries that let you do homomorphic encryption, they can build these things. And then also, people who want to build user-facing products can take SnarkyJS and incorporate it in their products pretty easily. And in this way, we hope to kind of get what it seems the JavaScript ecosystem has got, which is, sort of people who are way down in the weeds, working to make tools that people who are kind of, at the surface, trying to build user-facing products can use. And the result is that the user-facing products are usually pretty cool. Here are a couple of libraries that people have worked on in the ecosystem. We have this one's from Gretzky. This is ZK app data types, and it includes lots of things, but JSON parsing is maybe the most interesting thing. So we can parse JSON, right in the circuit and prove that we've done it all correctly. We also have El Gamal from Trevo. He also works at Owen Labs, but has done this, I think, kind of on his own. So this is a partial homomorphic encryption scheme that you can use for things like private voting or also proving like cosine similarity of two encrypted things. So this could be cool if you wanted to build something like a matchmaking service based on people's browser history without revealing, what their browser history was. And then we have, even more complicated, we have ZKFS, which is an off-chain storage library that an organization called Stove Labs is working on. And so it seems like every week there's, a cool library that somebody, pops in the Discord or something that enables new stuff. And that's the idea. So if you want to build libraries, this is an awesome place to do that. And the other reason that we chose JavaScript is because a lot of people use software that's written in JavaScript. And most of the interesting zero knowledge use cases, I think, are going to end up requiring that users generate proofs in their browsers. So how does all of this work? SnarkyJS is a TypeScript library. It's implemented in OCaml, Rust, and TypeScript, but everything eventually compiles into JavaScript or WebAssembly. Data is represented in one of the SnarkyJS types. All of these are ultimately represented as the field type, under the hood. And then SnarkyJS provides arithmetizable functions that are compatible with these types. That just means, if we have like an add function, then we have a way to SnarkyJS kind of knows how to represent that add method in a kimchi arithmetization. Then when we run this code, a witness is generated, when we invoke SnarkyJS code. And then SnarkyJS can generate a verification key from the arithmetization, and it can generate a proof from the witness and the verification key, I guess. And so you can yeah, write programs, prove them, verify the proofs, all inside of JavaScript, all inside of SnarkyJS. This also means that, yeah, you don't need a lot of developer tools, and that kind of goes back to this, everything is TypeScript thing we talked about earlier. You can use the tools you're familiar with, and you don't really need very many new ones. Now we'll spend a little bit of time talking about the Mina protocol. SnarkyJS was built with the Mina protocol in mind. And while it's true that the Near Foundation is looking at potentially building an integration in the future, because Mina and SnarkyJS work together today, you can expect to deploy whatever you build in this hackathon to the Mina network. Mina is an L1 blockchain that proves its entire finalized state using recursive zero-knowledge proofs. What we can see, what this means is that Mina stays a constant size over time, or I guess the amount of information required to verify the finalized state of Mina stays the same size over time. This is different from other blockchains, which effectively require all of the transaction history in order to be able to verify recent transactions. And there's a couple of cool reasons for doing this, but again, we'll kind of, it's out of the scope of this presentation for now. So how do developers write how do developers write smart contracts on Mina? They write them in TypeScript, and they deploy just the verification key to a ZK app account. So we make a transaction, we send the transaction to Mina, and then Mina has the verification key. Users run the smart contracts in their browser, and then they generate a zero-knowledge proof of their interaction after the verification key is deployed. And so you can see, if I'm a user, I run my application, it's just TypeScript code, we get a zero-knowledge proof out, and then we send the zero-knowledge proof to the Mina protocol. And if the zero-knowledge proof is valid, then we accept the transaction, and if it's invalid, then we drop it. So yeah, if the Mina blockchain can validate this zero-knowledge proof, then we commit any of the relevant state updates, and if it can't, then the transaction is dropped. So into our smart contract method, we're going to take some arguments that the developer provides. We're going to take some smart contract state from the Mina nodes themselves, and also some value from some values that represent things like block height, other things like that. And then we're going to run our computation, prove it, and we're going to get out a proof, and also some updates to the state of the smart contract and some updates to the state of the world. So this means the smart contracts work quite a bit differently. Instead of sort of requesting that computation be done and then having a bunch of nodes in the network do this computation, we do the computation ourselves, we prove it, we say what state we want to change, and then we send this proof and the state change to the Mina network, and the Mina network verifies it and applies the state updates. So that's all for Mina. There's a lot more there, but again, the point of this is to help get people started writing code in SnarkyJS. So, okay, we're going to build Wordle, and then we're going to make it recursive, but we'll start by building it sort of naively. If you don't know, Wordle is a game where there's a secret 5-letter word. And if I'm playing Wordle, then my goal is to guess the 5-letter word in as few moves as possible. For every guess that I provide, I either get back a gray hint, which means that that letter is not included in the word, or I get back a yellow hint, meaning that that letter is included in the word, but I guessed it in the incorrect place, or I get back a green hint, meaning that that letter is both in the word and also I guessed the letter in the place where it occurs in the word. And so we can see here, we start by guessing bears, we get R, so we know R is in the word. Then we guess groof, and we get, G is not in the word, but roof is the last 4 letters of the word. And then eventually we guess proof. And that's the word. So once we get 5 green hints, then we've won the game. And if we can do this in under, let's say 6 moves in this case, then we win. If it takes us more than 6 moves, then we lose. So we want to represent this word, this 5-letter word, and we don't have a type for this. And so what we can do here is we have this, struct, and we can extend it to create a word. That word can store this array of 5 field elements. And actually, before I kind of get started on this, maybe it's worth saying the point of this sort of presentation is to be somewhat educational, but mostly it's just to give you a lay of the land. And so if some stuff slips through the cracks, that's entirely fine. There's going to be a reasonable amount of code. That's a double-edged sword. The advantage is that you get to see a lot of what we have. The disadvantage is that sometimes it's not as easy to follow as it could be. So If you lose track of anything, don't worry. There's going to be a QR code and a link at the end of the presentation with links to the slides, the code, and more information. And also you can, of course, contact us with any questions after the presentation. And we're looking to hopefully have some time so that people can ask questions. So anyways, back to where we were. We are going to create this word by extending struct, and it's going to have an array with 5 field elements. And so these field elements can, store something that represents a number, basically. I'm sorry, a letter, in this case, a value between 1 and 26. And we're going to add this static method on that takes in a word, which is a JavaScript string. And we'll take the JavaScript string, we'll make it all lowercase. We will check that all the letters are actually letters. And then we'll grab the ASCII code, subtract 96, and dump them all into this encoded word array. And then we'll return a new word that includes this encoded word. So we have a static method that we can use to generate one of these words from a string. And then we also have a method hash, which will actually take the hash of this encoded word. When we have one of these words, we can call the hash method, and we'll get back the hash of the word. And so you can see for this, we just call, Poseidon.hash, and then we pass in our encoded word. Poseidon.hash takes in an array of field elements and spits out a single field element representing, like the digest of whatever we stuck in there. So now that we have this type that we can use, we can, get started thinking about what we actually want to do in our smart contract. And we create this smart contract by extending a smart contract and making a thing called Wordle. So we have a smart contract called Wordle now. And the first thing that we'll do is we'll define some state that's going to live on chain. And this state is, if whenever we change the state, we prove that we're allowed to change the state in the way that we are. This is what this state decorator at the beginning here does, is it basically tells, SnarkyJS, hey, this value, you should store it on chain. And also when people change it, make sure that they're changing it in a way that sort of is in accordance with the rules of the smart contract. So first things first, we get, solution hash. This is just a field, and this is the hash of the solution that we chose, the secret word that we chose. And we're going to store this on chain so that we can check that the hints that the hint generator provides are valid. And we can do this without revealing the word. I guess, there's not that many combinations, so maybe we should have added a salt to it too. But for the sake of simplicity here, we didn't. So we're going to store our solution hash on chain. Then we're also going to store a turn number on chain. And you can see this is an unsigned integer of 32 bits. And the reason is because we want to use the mod method on this, right? We want to be able to just check, is it my turn or the opponent's turn, really easily. And so it's easier to use, this 32-bit unsigned integer than it is to use a field in this case. The final thing that we're going to store is our last guess. And this is the word struct that we just defined. Last guess is going to be of the word type. And it's going to store the word that the player guessed. It's also going to be updated after the hint generator plays. And so we're going to add 200 if the letter is correct and in the correct place. And we're going to add 100 if the letter is correct, but in the incorrect place. And so this way we can use a single on-chain word, and we can, have the generator, the guesser, update the word, and then the hint generator can only mutate the word in this predefined way. And because we've chosen to encode, A as 1 and Z as 26, we can add 100 or 200 and not lose any information. So we only have, 3 pieces of state here. And then we're also going to have 3 methods. The first is this init method. And this is used to set up the smart contract. It should be invoked after the contract is deployed, but before any user interaction. So hopefully, if you're deploying a real smart contract, you in your deployment script or whatever, also call this init method. Then after the init method is called, you can let people call the other methods on the smart contract. So then we have this publish guess method. This accepts a guess. It's of type word. And we invoke it when a user wants to publish a guess. We add this method decorator at the front. This, again, just tells us this method is something that's basically like a smart contract method. We can, we expect users to call this, and when users call it, they can prove that they did so correctly and get, something out of it that they can put into a transaction. We also have this publish hint method, sort of the same thing. We pass in a word, but this time it's not our guess, it's actually the solution. So we pass in the secret word. The idea is that the hint generator knows the secret word, and they want to generate hints based on the secret word, but without revealing what the secret word is. And so any arguments that we pass into these methods are secret unless we do something that makes them not secret inside the method. Right? All of this code runs on the user's browser, and so we can throw whatever we want to into our method calls, and we get a proof out that doesn't reveal anything. The only instance in which something is revealed is if you either reveal it deliberately or if you need to have some kind of outcome. Like if you need to update state, you have to find a way to, you can, for example, hash the state and store the hash version of the state on chain. Okay, so let's jump into the init method. The first thing that we're going to do is we're going to set the solution to the word to hello. And so this is pretty straightforward. We call, this solution hash set. And so, we can call solution hash here. I'm sorry, we can access solution hash through this because, we used the state decorator earlier. We can call the set method, and then we can pass in any value that we can set to a field. Solution hash is a field. And so what we do now is we use our word struct. We call the from string method on it. We pass in the JavaScript string hello, and then we get the hash of that by calling the hash method. And so we get out of this a field of the digest of the hash of the word of the string hello, and we set that to solution hash. Then we set the turn number to 0. So same idea, but now we're going to create a new unsigned integer of 32 bits. We're going to set that equal to a field, and we're going to set that field to equal to the JavaScript number 0. So we can pass JavaScript numbers into this field, and then we can pass fields into this unsigned integer, and then we can pass this unsigned integer into the set method. Finally, we want to set the initial guess to and the reason is it doesn't matter what this is. It won't be possible to generate a hint until the guesser updates this anyways, because the turn number will be 0. But same idea, we call the from string method on word, and we pass in 5 A's. So when this init method is called, what it's going to do is execute all of this, and the end result is going to be that now the on-chain state for the smart contract will reflect the values that we've set here. So after the init method is called, now we can start looking at this publish guess method. This is what people will call when they want to publish a guess. So the first thing that we want to do, we'll kind of just run through what we're going to do first is, we're going to grab the turn number from the MENA network. The MENA network stores the state, and we run the smart contract in our browser. So in order to do something, we need to grab this state from the MENA network. The next thing that we're going to do is we're going to check that it's the guesser's turn. Then we're going to increment the turn number, and then we're going to check that all the values are between 1 and 26. This just means, that the values that we passed in represent a valid letter configuration. Then finally, we're going to set last guess to new guess. So this is fairly straightforward. We'll start with the turn number. What we can do is, we can call, get on this turn number. And what this will do, and it sort of, there's a little bit more to this. It's not as naive as when we call this, we just contact a MENA node directly and grab the value. There's some like memoization and stuff. But generally, you can basically think of it as what this says is grab the value of this variable on the smart contract that we're running this code in from the MENA network, and then just set it to this variable. So we grab the value from the MENA network, and that's sort of one half of the equation. When we run the code ourselves in our browser, we need to get the value because what we do in this method depends on it. But the other side of this equation is that once we actually have a zero knowledge proof, right? Once we've ran the code and proved that we've done it correctly, we could do something like wait a very long time, say like a week, and even though the zero knowledge proof is valid, now the turn number on the blockchain is changed, and so we have a valid proof, but the proof sort of doesn't make sense anymore because we have a different state on chain. And so that's what this second line does. This just asserts that the turn number on chain is equal to the turn number that we have here. Or sorry, that was backwards, that the turn number on chain is equal to the turn number that we have here. And this way we, grab the value, run our code, do something with it, get a proof. But then if the values that our execution of the code is sort of contingent on change, then the blockchain will just drop our transaction when we send it, because the preconditions for it are no longer valid. The next thing that we'll do is we'll check that it's the guesser's turn. So we can just take turn number mod 2, and then assert that this is equal to a new unsigned integer of value 0. And this assert equals method here, all that it does is it basically creates a constraint. So if we try to run this code and this condition doesn't hold true, A, the execution will halt, we'll get an error. B, even if we find a way to override that, we won't be able to get a valid zero knowledge proof. And so we have some other methods that will, do things like check equality and return like a Boolean. But in this case, we're just sort of creating a constraint directly. The next thing that we can do is, so in other words, sorry to touch back on this again. If it's not the guesser's turn in this case, the guesser simply can't generate a valid proof. The next thing that we do after we've checked that it's our turn is we increment the turn number. So we just set the turn number equal to the current turn number plus 1. Pretty simple. The next thing is to check that all of the values that we've passed in our guess are valid letters. And we can do this pretty simply. We've got a for loop, and we're going to check for every value in the encoded word. Is it greater than or equal to 1? And is it less than or equal to 26? And so again, these asserts are creating constraints. They're not sort of checking things and returning values. They're just creating constraints directly in the circuit. Finally, what we're going to do is we're going to set last guess to our new guess. So we'll call set on last guess, and we'll pass in the guess that we got here. So really all that the publish guess method does is that it checks that the conditions are valid such that we can update the guess, and then it updates the guess to whatever we pass in. Pretty simple. Now, when it comes time for the hint generator to create a hint, we want to be able to prove that they're creating a valid hint. But we want to be able to prove this without them disclosing the secret word that they have decided on as the sort of solution to the game. And so the first part of this code, we'll do sort of the same thing we did last time. We're going to grab a turn number from the MENA network. We're going to check if it's our turn. We're going to increment the turn number. And then we're going to grab the solution hash from the MENA network. And we're going to check that the solution hash that the solution hash on the MENA network is the same as the solution that we pass in. This way we can't pass in, a fake solution. We've committed to the solution when we started the game. The next thing that we'll do is we'll check that our solution matches the one on chain, and then we'll grab the last guess from the MENA network. Then we'll do some stuff. And so, first we'll kind of make sure that it's okay to do stuff. We have just a bunch of sort of conditions, and then we can do stuff. So we'll get started on the conditions for now. What we can do is, sorry, I'm just checking time real quick. We can grab the turn number from the MENA network. Same thing as before. We grab it with the get method. We assert that it's equal to the value at the time that the proof is verified using this assert equals. Basically the same idea. We are checking if it's our turn, but we add 1 this time so that, when it's the hint generator's turn, it's not the guesser's turn. And when it's the guesser's turn, it's not the hint generator's turn. Pretty simple. We'll increment the turn number exactly the same as in the publish guess method. We'll grab the solution hash from the MENA network. pretty much the same idea as up here when we grab the turn number. Just now it's with solution hash. We'll check that the solution we provided matches the one on chain. So we'll take our solution hash that we passed in, and we will we'll take the solution hash that we grabbed from the Mina network, and we'll assert that it's equal to the hash of the solution that we passed in. Let me see. Okay, sorry. Zoom is a little bit unhappy with me, I think. So next, we will grab the last guess from the Mina network. Same idea as up here when we grab the turn number or the solution. And now we're ready to do some stuff. So the first thing that we want to do is we want to add the hints for the green letters. And this is fairly simple. We'll just iterate through every index in our word. And I think it's recording again, it sounds like. So, okay. So sorry, where were we? If the letters match, then we will add 200 to the letters in the last guess. So we take our last guess, look at the index that we're iterating through, and then we set it equal to the circuit.if is correct position. So if is correct position is true, then we'll return this first value. And if is correct position is false, then we'll return the second value. And so the first value is the last guess with 200 added to the value in this index. And the false return value is just the same thing that is in encoded word now. So in other words, what we get out of this is encoded word on last guess, but now anywhere that we have matching letters with the solution that we passed in, we've added 200. So if we have, A is 1, and this is in the correct position, then now we have 201 in that position. The next thing that we do is add the yellow letter hints. And this is very slightly more complicated, but not a whole lot more. We're going to iterate through every combination of indexes this time. So we just have a nested for loops. And we're going to check if the letters at these indexes match. So again, exact same thing, does letters match is going to be equal to true if the last guess and solution match for the I and J indexes this time. So, we'll step 1, go through step 2, go through, and so on. And we'll check if these match. And if they do match, then we can add 100 to the letters in last guess. This is the same thing we did for the green hints. If the letters match, we add 100. If they don't match, we return the same thing. But then what we want to do is we want to make sure that we're not counting letters twice, as you would if you sort of did this naively. So what we're going to do is we're going to set the values in the solution to 0 if the letters match. This way we don't count them twice because, it's impossible to set these to 0 any other way. The only way that these values can be set to 0 is right here. And when they're set to 0, this is outside of our range of 1 to 26. So they're not letters anymore. This is kind of like a null value. And so we can know that nothing will match this. And so what we do is if the letters match, we return 0 and set that equal to the J index in solution. Otherwise, we just return the I index in solution and set that equal to the J index in solution. This way we count the letters only once. The last thing that we do is we set our last guess equal to our new last guess, which includes the hints. Pretty straightforward. Everything we did back here, mutated this last guess, and then we just set it. So this is a smart contract. You can test this or deploy this to the Mina network today. The code is at the end of the presentation, and yeah, you can go deploy this yourself. But what gets very interesting is, when we add a recursion to this, Mina has the ability to run smart contracts that can take zero knowledge proofs as inputs to methods. So we can have a method in a smart contract on Mina and pass in a zero knowledge proof of some execution that happens outside of a smart contract, and we can verify it. So we'll get into this pretty quickly. whoops. This is a very simple ZK program. ZK program is the API that we use to create these, provable programs, as opposed to smart contracts. These are literally just programs. And so you can think of a smart contract as sort of like a superset of a ZK program. It's a ZK program, but it also has stuff to manage state and other sort of blockchain stuff. These ZK programs are not related to the Mina protocol. They're literally just provable programs. You can write them, prove them, and verify them all inside of your browser. So you could do something like make a peer-to-peer application that use these. And here's a really simple example of a ZK program. So this is called add1. It does what it sounds like. We have a public input, which is of the type field. And then we have two methods. One is base case and one is step. And so for base case, we take no private inputs, and we take one public input, which we have up here. And this public input is of the type field. And what we do is we assert that the public input is equal to 0. And that's all. And so the next method that we have is the step method. And this takes as a private input a self-proof. And when we call this method, we can pass in our public input, which is our field. The same thing is up here. We can also pass in this earlier proof, and this is private this time. And what we can do is we can verify this earlier proof right inside of this also provable method, and then we can access the public input of the earlier proof. So when we run, in this case, our base case, what we get out is a proof that we ran base case correctly, and we also get a public input, which is accessible from then on. And so what we can do is we can add 1 to this, and then we can assert that this is equal to the public input that we passed in here. And so what this means kind of practically is that after we've written a program like this, we can first take our ZK program and call the compile method. And when we do, we'll get back a verification key. Then we can call the base case method on this and pass in a field with a value of 0. And you can see that the base case method basically just checks that whatever we pass in equals 0, and then stores this. And so once we've done this, we get out a proof. And then we can take this proof and we can pass it into another invocation of the step method, this time on the add1 ZK program. And so the step method is going to take in our value, and this is just whatever the last value was plus 1. So in this case, 0 plus 1 is 1, but it's also going to take in the proof that we had last time we ran it. And so what we get out is a new proof. This proof is called proof 1. And we can kind of see what this looks like. When we take the base case and run it, we get a proof where public input is equal to 0. Then when we pass this proof into the step method and also pass in a public input of 1, we check that the public input of 1 is equal to the public input on our proof that we passed in plus 1. And so if that holds true, then we get a proof of the step method, but now the public input on this proof is equal to 1 instead of 0. And so then we could pass that proof back into step again, and we could pass in 2 this time, and everything would hold true, and we'd get out a proof, exact same thing, but now public input is equal to 2. And so we can do this over and over and over again. And the proof stays the same size. It's the same computational complexity to verify, and it's basically, in this case, the same computational complexity to generate. So this is super cool and super powerful. We can do this, over and over and over again. And I can give anybody a proof at any point in time, and they can know that I came to this proof by doing what we describe here. The next thing that we can do is, if we define a SnarkyJS smart contract, we can pass these proofs as arguments into methods on the smart contract, and we can verify them and assert that the verification is true inside of the smart contract method, and then we can do some other things. And so this is super powerful because this enables applications to work a lot differently. In the context of blockchains, what this means is that if I want to do something like have a game, usually I would write a smart contract, I would deploy the smart contract to the blockchain, and then users would create transactions, send the transactions, the blockchain would mine the transactions, and then the user would pay a fee. And so in this exchange, the user has to wait for blocks, and they also have to pay fees every time that they make a move. And so this is a bad user experience, and it's prohibitively expensive for a lot of interesting games. What's possible using recursion like this is that, let's say that we have like a two-player game, like Wordle, for example. We have a hint generator and a hint guesser. If I'm the hint generator, what I can do is I can create a proof that says that I generated a valid word, and I set the game up correctly such that the current turn is set to 0, such that the solution hash matches my word, and also there's one more piece of state, but it'll be in the next slide. Anyways, I can prove that I've set the game up correctly, and then I can send this proof to you, the player, and the player can verify the proof that says that the word generator is basically playing, in accordance with the rules, so that they know that they're not playing a bogus game. But then what they can also do is they can make their move, prove that their move is valid, verify the proof of the last move, in this case, the sort of like initialization move, and then they can send this proof back to the hint generator, and they can go back and forth this way. And at the end, they have a proof that attests to the fact that every single move was made in accordance with the rules of the game. And this proof can be validated inside of a smart contract method. But the key is that the users in this case don't have to pay transaction fees, because they can send the proofs, amongst themselves. And they also don't have to wait for blocks to be mined. It's just a peer-to-peer communication. And this is really cool in the context of blockchains, because it lets you do things like build something kind of similar to app chains. We call them application-specific rollups, but it also just opens the door to kind of a lot of instances where people are using blockchains where they don't need all of the sort of guarantees that blockchains provide. A lot of people are using blockchains just for verifiable execution, and you can actually do that without a blockchain. In this case, you can prove whatever you want to, and if you need to anchor it into time, or sort of like if you need things like sequencing and data availability, you can put it on a blockchain. But if you don't, you can just send it to you can send the output of your computation plus a proof to whoever wants to check it. So sorry, that was a little bit rambly. Here is the same thing we had earlier. This is a struct per word. Nothing changes here. This is just a type. Everything is the same. But something does have to change here. So we have this state that we stored on chain before. Well, we can't do that anymore because there's no blockchain in this model. We have the same values, but this time we're actually going to create an additional struct called Wordle state, and it's going to store these values. So we have solution hash, turn number, and last guess. And this is important because we actually need to send the state amongst ourselves and remember what it is now that we don't have a blockchain. At the end of the game, we can do something like take our proof and verify this inside of a smart contract method if we want to do something like get a payout in exchange for winning a game. But we'll jump back to that at the end. For now, we store our game state in this Wordle state, and we exchange it between our two players using a peer-to-peer method. Now we have our ZK program. It's called Wordle Recursive, and we can kind of see what it looks like. We have a public input, and this is Wordle state. This is the thing we just defined. It stores the state of the game. It's the same as the public state on the Mina blockchain. Then we have some methods. They're the same methods. We have an init method, a publish guess method, and a publish hint method. And we can see that the init method doesn't have any private inputs. It doesn't, really do anything except for sort of ensure that the values in the Wordle state are what they should be. And so we take in a Wordle state, we basically check that all the values are what they should be, and if they are, then we generate a proof. The publish guess method does have some private inputs. It accepts a word and also a self-proof. And so the self-proof might be a proof that we got from running the init method or the publish hint method. The word is the same thing as we had on the smart contract method. It contains our guess. And then, when we look at the method down here, we take the previous proof as an input, we take the guess as an input, and then we take Wordle state as a public input. And so roughly the same thing happens down here for publish hint, but now our word is the solution. We still take a self-proof as a private input, and we verify it. So let's check out the init method first. The init method, we're going to do pretty much, you can see this looks almost exactly the same as it did when it was a smart contract, except for that there are a couple things that have changed. Sorry, this is the same code as we had in the smart contract. You can see we call the set method on our state, and we set it. So what's changed in the ZK program version of this method is that now we have private inputs array up here. It's empty, so none of our inputs are private. And then we have inside of our method, we pass our Wordle state, which is public and represents the state of our game. So instead of being able to access this by calling some kind of method, we pass it in as an argument. And then there are some other things that are different here. And this is that we're calling assert equals instead of calling set. And so how this works, right, is that we're passing in the Wordle state. The Wordle state is just, a struct. It's, a thing that we can just sort of like mutate as we want to. But if we pass in a Wordle state that meets these initial conditions, then we also get out a proof. And so we get a proof, and that proof contains this public input, Wordle state. And so in order to start the game, what we do is we generate a valid Wordle state for the start of the game. We pass that Wordle state into the init method. If all these assert equals hold true, then we get out our proof. And then we have a proof that includes the Wordle state. And that's the start of our game. We have, the first proof in our game, and that proof contains the initial Wordle state. So set has turned into assert equals, because instead of setting the values on chain, we're asserting that the relevant value in our public Wordle state is equal to the correct value. Now we can check out the publish guess method. We can see that this takes in a word and a self-proof. The word is our secret, the word is our guess of what the secret word is. And the self-proof is the proof that we got from running either init or publish hint. We take in the Wordle state, this public value, and this can be got either, we can grab this from the proof that we got by running the last method. By calling on the proof, we can just access the public input. Then we have our guess, which is private in this case. And then we have our previous proof, which is also kept private in this case. And so what we do is we verify that the previous proof is valid just by calling this verify method on it. Then we get our term number, but again, we can't grab it from the blockchain anymore. And so what we do is we use this previous proof that we passed in. In this case, let's suppose that it came from running the init method. And we, grab from public input the term number. And this is stored if we go back all the way here. This public input term number, we've asserted that it meets some condition. And so we know that this term number is the same term number that we know that the term number is valid because we're grabbing it from the proof. And we know that the proofs can only be generated by running one of these three methods. So Then what we do is we can check that it's the guesser's turn. And again, this is sort of the same concept. Instead of, we call the assert equals method, and we assert that our turn number, in this case, we grabbed it just from the last proof, meets these conditions. We assert that our new turn number is going to be equal to our turn number from the last proof plus 1. And we also assert that our last guess, that's included in our last proof is equal to the new guess that we passed in up here. And so these changes are basically the exact same changes that are made to publish hint. You can see that this code looks exactly like it did when it was a smart contract, but now it's a ZK program. We only have to change a couple things. We're specifying private inputs, we're passing in a proof, we're verifying the proof, and then we're accessing the values a little bit differently. Instead of grabbing them from change state, we're grabbing them from previous proof. Other than that, it's exactly the same idea. And instead of changing state, we're changing this public input. Other than that, it's exactly the same thing. And so we do the same thing to publish hint, but I'll spare you, from that for the sake of time. And that's all. We can run this now, and we can, run init, generate a proof, run publish guess, generate another proof, run publish hint, and so on and so on. And as we do this, we only have to remember the last proof, and that proof verifies the proof before it, and that proof verifies the proof before it, and so on and so on. And so we can play this whole game just by exchanging the most recent proof and our Wordle state. And we can know that our Wordle state is valid by verifying the proof. So, when we run this, what does it look like? Well, we need a couple of helper functions that basically do that handle doing things like adding 1 to the turn number in the state before we pass it in. And so these are pretty simple. Again, we won't touch on these, but they're in the GitHub repository, which will be linked to at the end. And so we call this helper method. It just makes it easier to kind of run through it. We call the helper method for init, and then we get the initial state after running init. Then we can take this initial state that we got, and we can pass it into our init method on our actual ZK program. And what we get out is an initial proof. Then we can, in this case, set this guess variable equal to a word of the value exile. And we can take our guess and our initial proof, and we can pass it into this publish guess method on the Wordle helper. And so again, this helper, we didn't define it here, but it's really simple. It's literally just taking the values from last proof, doing the same thing that we do inside the, that we would do inside the smart contract to figure out what the new values would be, and then spitting out a new state, a new user state after we've done this stuff. And so then we take this new state and we pass it into the publish guess method on the recursive Wordle ZK program. And we also pass in our guess and also our initial proof. And so we verify the initial proof. We check that our guess meets the required conditions. And then we also, or if this is valid, then we set everything equal to user state. Now, it's time for the server to play, and the server can do basically the same thing. It can call this publish hint method on the helper, pass in the proof that it got from the guesser, as well as the solution. It will return something that looks like this. I think it's called a nullish coalescence in Typescript. Is here just in case this value is undefined. But it also is here because it lets us see easily sort of the shape of what's returned, which is if everything goes according to plan, what we get back from this is a solution hash where the word is equal to hello, the turn number is equal to 2, and the last guess is equal to exile. With this state, we pass it into the publish hint method on the recursive Wordle contract, And we also pass in our solution and our user proof. And so the solution is kept private. The user proof is also kept private, and the server state is made public. And so we check that the last proof is valid. We check that the solution matches the hints that we get in the new server state. And if all of this is true, then we get another proof out. And we can do this over and over again. So this is a super powerful pattern. And there's other things that you can do. You can do things like have smart contracts that accept proofs of themselves. You can do things like, you can have ZK programs that accept proofs of the method that you're calling. So you can have a method that accepts a proof of the same method. You can also have, for example, a smart contract that verifies a proof generated from a ZK program. You can have sort of a situation where you could have many different proofs all aggregated into one. You can have basically one ZK program that is designed to verify the proofs that are generated by, like, say, 5 different other ZK programs. You could do something like have like some kind of crazy like MapReduce sort of architecture where you could send out like, we want to do this computation on a bunch of different machines. Then we want to grab all these proofs, aggregate them, and just do this until eventually you get one proof. And so you could do something like prove that the moving average of some large amount of data is correct in this way. And yeah, a really interesting pattern is that we can take the proof that we get from running a ZK program, and we can pass it as an argument into a smart contract method, verify the proof, and then do some other things. So in the case of our Wordle example here, we can let the users play the Wordle game. And if one user wins, then they can send their proof to a smart contract and get some kind of payout. Or you can have, like another rule such that if, let's say that there's an unfinished game, one user stops playing, you can have something like a timeout rule such that after, I don't know, let's say 1 hour, if a user hasn't made a move, then you can submit any proof, and whichever proof has the highest number of moves after 1 hour claims the prize by default. So okay, that's I think pretty much everything on recursion, and now we can talk a little bit more about the hackathon. We have prizes at $4,000, $4,000, and $2,000. So 2 first prizes and 1 second prize, basically. Applications, libraries, and integrations are all fair game. If you are thinking of doing something crazy, you should definitely talk to us, and we can tell you if it's good or not good, and if you should do it. But you should definitely talk to us because we're interested in hearing crazy ideas. The Owen Labs team will end up judging, and you can reach out to us with any questions, again, regarding like what's eligible, if you're just curious what you should build, if you just sort of want to talk, if you're not sure you want to do our track or somebody else's. All of these are fine reasons to reach out to us, and there will be information on that in just a second. And so I guess the final question is, how do you get started? And the answer is pretty simple. You can just npm install global, the ZK app CLI. This is the only piece of dev tooling that we have for Mina. It's super easy to use and straightforward because it's not managing as much stuff as something like Hardhat would be. Then you can call it ZK project and put in whatever name you want, and you'll get a whole smart contract with some scaffold code, and then you can explore that using the IntelliSense, like we said earlier. It's pretty easy to deploy it to Berkeley. The testnet, Berkeley is the Mina testnet right now, so you can do that. Or you can also write applications that use just ZK programs and don't use the Mina blockchain at all. Finally, we have some next steps, notes, and contact information at this short link, which hopefully one of my teammates will post in the chat. Otherwise, I will in just a second. Or you can scan the QR code. It'll take you to a Notion page where you can find the slides. I'm not sure if they're there yet. If they're not, I'll put them on after this call is done. You should be able to find ways to talk to all of us and some more information. So with that said, I think that's all. Thank you, everybody, for listening to us. The Owen Labs team will end up judging, and you can reach out to us with any questions, again, regarding like what's eligible, if you're just curious what you should build, If you just sort of want to talk, if you're not sure you want to do our track or somebody else's, all of these are fine reasons to reach out to us, and there will be information on that in just a second. And so I guess the final question is, how do you get started? And the answer is pretty simple. You can just npm install global, the ZK app CLI. This is the only piece of dev tooling that we have for Mina. It's super easy to use and straightforward because it's, not managing as much stuff as something like Hard Hat would be. Then you can call it ZK project and put in whatever name you want, and you'll get a whole smart contract with some scaffold code, and then you can explore that using the IntelliSense, like we said earlier. It's pretty easy to deploy it to Berkeley. The testnet, Berkeley is the Mina testnet right now, so you can do that. Or you can also write applications that use just ZK programs and don't use the Mina blockchain at all. Finally, we have some next steps, notes and contact information at this short link, which hopefully one of my teammates will post in the chat. Otherwise, I will in just a second. Or you can scan the QR code. It'll take you to a Notion page where you can find the slides. I'm not sure if they're there yet. If they're not, I'll put them on after this call is done. You should be able to find ways to talk to all of us and some more information. So with that said, I think that's all. Thank you, everybody, for listening to us.